In this video, I'll be unboxing all of my past engineering exams to give you a better picture of what engineering exams are like and what to expect. I wish someone had shown me what a typical engineering exam is like when I was a freshman. So in this video, I'll be walking through 3 of my more challenging exams and showing you the different types of formats, types of questions asked, what my solutions look like, my grades, and several strategies that you can use to help maximize your score right off the bat. We'll go in chronological order and first look at my multivariable calculus exam from the spring semester of my freshman year. For general math and physics courses, the first page of the exam will look something like this and shows the number of questions and breaks down how much each question is worth. In my case, there were 10 questions and each question was worth 10 points. We had 2 hours to complete this exam and it was administered in a big lecture hall. We were also allowed to bring a calculator, but cheat sheets were not allowed. Generally, math and physics courses will provide a formula sheet containing all of the formulas, trig identities, and rules needed to complete all of the questions. The first page of the exam asks us to evaluate a double integral given a region bounded by a circle whose equation is x squared plus y squared equals 16. Integration is a fundamental concept in engineering that can be used to calculate various quantities such as area, volume, center of mass, moment of inertia, and thermal energy storage. The integral sign is represented by this wavy line, and these numbers represent the region over which the integration is performed. I used change of variables, the Jacobian, and then polar coordinates to solve this first question. I try my best to show every step and keep my work clean and easy to follow so that the grader can give me as much partial credit as possible if my solution is not entirely correct. Moving on, question 2 has 2 parts. The first part tests us on scalars, vectors, and cross products, and notice it's a short answer question. For these types of questions, always remember to explain your reasoning and justify your answer. This is a classic engineering exam question format where one question has multiple parts that test you on related concepts. The second part of this question asks if these 2 lines are parallel. I find the direction vectors for each line by taking a derivative, and since they are scalar multiples of each other, the lines are parallel. I underline my final answer to help the grader out since they are grading hundreds of exams. Moving on, question 3 again asks us to evaluate an integral. This question is fairly straightforward that I solved by simply plugging and chugging into my calculator. However, I did lose 3 points on this question because I didn't show all my work and made a small mistake when inputting the limits into my calculator. Question 4 provides a double integral and vertices of a tetrahedron and asks us to come up with an equivalent triple integral. Sounds daunting, but this question is simply testing us on the divergence theorem to see if we know how to apply it. Moving on, question 5 is another 2-parter. The first part asks us to evaluate another triple integral. The key to answering this question correctly is converting Cartesian coordinates to spherical coordinates. Notice I write a brief sentence here with an arrow pointing to the integral explaining we are integrating over a sphere of radius 3. It turns out I got this question right, but during the exam I wasn't too confident in my final answer, so I wanted to give the grader as much information as possible to maximize the amount of points they give me if my solution turned out to be incorrect. For the second part, I had to find an equation of a plane containing the point 0, 1, 0, and that's not intersecting the xz plane, which was pretty straightforward. Notice I always try to box or underline my final answer so there's no ambiguity. Moving on to question 6, we had to determine whether the limit exists using the 2-path test. The limit of a function exists if the limit is independent of the path taken to the limit point. Now question 7 provides a double integral and asks us to sketch a solid that it represents. You'll find that multivariable calculus involves a lot of complex shapes and volumes bounded by different geometries and requires you to visualize them in your head. I spent way too long on this question, but luckily I got full credit. Technically, I could have sketched this solid and moved on, but I probably wouldn't receive any points if my answer turned out to be wrong. So I decided to write a paragraph explaining my thought process. Question 8 is similar and required us to visualize and calculate the area of a complex geometry using integrals and parametric equations. Like always, a good habit is to box your final answer. Next, question 9 was the hardest problem for me, where I had to prove that an ellipsoid and sphere are tangent to each other at point 112 using a series of rules, conditions, and assumptions. Last but not least is question 10, which had two parts. The first part asked us to find the partial derivative with respect to z. Like integrals, derivatives is another fundamental calculus concept used to find the instantaneous rate of change of a quantity like position or velocity. Partial derivatives measure how a function changes with respect to one variable while keeping other variables constant. For instance, the temperature in a room can depend on the position in the room and the time. The second part then asks us to find a directional derivative, which measures the rate at which a function changes along a specific direction. As you can see here, this exam had 10 questions and we had approximately 1 or 20 minutes to finish it, so I had to pace myself. I made sure to spend no more than 12 minutes on each question. My final score was a 92 out of 100 or a 92%, and the class average was at 80%. This exam was worth 30% of our final grade. I needed to do particularly well on this final exam because I scored below the class average on a previous midterm exam. Remember to start with questions that are worth the most points, or if each question is worth the same amount of points, skim through the exam and start with the questions that you can answer right away. Now you might be wondering how I was able to score so high on this exam and how some students manage to get a perfect score. The answer is pretty simple. Just practice. Nobody is good at math or calculus when they're born. If you're struggling with these courses, it's just because you haven't done enough practice. Do the homeworks, practice exams, problems in your textbook, and review your mistakes. Now, it goes without question that practicing is essential, but it can be monotonous, so there's actually this very interactive and effective way that transformed my approach to mastering all of these concepts. Brilliant, the sponsor of today's video, is the ultimate platform for hands-on learning in math, science, and engineering. What sets Brilliant apart is its commitment to adding fresh content every month, ensuring a constant stream of exciting lessons. Whether you're starting from scratch or building upon existing knowledge, Brilliant tailors its content to your needs, allowing you to learn at your own pace on your phone, tablet, or computer. Having personally completed all of the math courses on Brilliant, I can vouch for its profound impact. The bite-sized lessons and well-structured learning paths not only helped me hone in on key concepts, but also significantly improved my information retention compared to traditional lectures. This approach unlocked my full potential in my classes, making Brilliant a key player in my educational journey. Their cylindrical and spherical integrals course was the key reason I was actually able to excel on my final exam. It connects complicated concepts like change of variables in the Jacobian to real-world problems like calculating the total mass of a storage tank or volume of a spacecraft parachute, so that these concepts are easy to understand. Try out everything Brilliant has to offer free for a full 30 days using my link brilliant.org/engineeringgonewild listed in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription. Now let's jump into this midterm exam for dynamics class that I took the spring semester of my junior year. This is a fundamental mechanical engineering course and contains a lot of calculus. For this exam, we were only allowed to bring a calculator and had 2 hours to finish it. There were a total of 4 questions, each worth 25 points, so I made sure to spend 30 minutes max on each question. The questions on this exam were ordered from easiest to hardest. I'm not sure if this was by design, but this does seem to be the case for many of my exams. For the first question, we were given a ball attached to a spring that slides in this radial groove and this circular plate that's rotating. We are first asked to derive the equation of motion for the ball and then the normal force exerted by the groove on the ball. The solution is pretty lengthy, so I won't go into all of the details, but I will talk about some tips and rules of thumb that you should know when doing these types of questions. First, always start off by drawing a schematic. Of course, there are questions where you don't need to draw anything, but for statics and dynamics, almost every every question will require one. Second, always number your steps like this and explain each step with a brief sentence or phrase. For example, for step 1 here, I first have to define the coordinate system. So here I write choose coordinates, which is rotating with the plate. This way the grader can follow your work and can quickly tell in which step you made a mistake if your final answer is incorrect. Even though my final answer was wrong, I only lost 1 point because I showed all my work. For my final answer, I wrote k over m plus omega squared times r sub x, when instead this plus sign should have been a minus sign. The grader could easily tell I fully understood how to do this question and simply made a foolish math error. Third, always box or underline your final answer. This is especially important for questions that have multiple parts. Let's move on to question 2. This question is similar to the first and follows the exact same framework. We are asked to calculate the maximum speed at which this car can travel on this circular incline road. For long questions like these, it might help you to write down all the givens and the unknowns to keep track of all the different variables. Most engineering questions will require you to make assumptions that you should also write down. So for this question, I start by drawing a schematic and defining the coordinates in step 1. In step 2, I draw a free body diagram that shows all the forces acting on the car. Step 3 shows Newton's second law, which we will use later on in this problem. Step 4 is defining the kinematics or motion of the car, which includes position, velocity, and acceleration. The final step is combining steps 3 and 4 and substituting all the expressions into Newton's second law to solve for an expression for the max velocity. Notice that I boxed my final answer, which is an expression, not a number. Next, question 3 was very involved, where we are asked to find the equations of motion for this orange block. I did lose 6 points on this question because I made some wrong assumptions, but all the solutions you see here are correct in case you were wondering how to do these problems. In step 2, I drew a free body diagram for the mass and both pulleys and find expressions for the small pulley force and the angular displacement of the big pulley. Substituting everything in and doing some manipulation, we get the equation of motion, which is a differential equation. The last question on this exam tripped up a lot of students and asked us to derive an expression for the height of this orange collar that slides up and down on a pool. This type of problem was never assigned on homeworks or talked about in lecture. It was challenging because we had to make many assumptions and introduce several constants and variables into the mix in order to get this question right. So my guess is that the professor quote unquote wanted to separate the men from the boys with this last question. The final score I got was a 98% and the exam average was a 73%. This exam was worth 40% of our grade. If you're looking at my exam and have no idea what's going on, that's perfectly normal. It might seem complicated, but once you start taking the course, things will start to make sense. Now let's take a look at my mechanical vibrations exam. This was an advanced engineering elective that I took the fall semester of my senior year and taught multi-degree freedom of systems like vehicle suspension systems and aircraft landing gears, as well as natural frequencies, modes of vibration, and resonance. Having a solid understanding of vibrations is crucial for designing automotive and aircraft systems and rotating machinery such as engines, turbines, and motors. The exam was 2 hours long and had 5 questions, each worth 20 points. This meant that I had 24 minutes max to complete each question. We were allowed to bring a 1-page cheat sheet that only contained formulas. This course presented many challenges and required students to have a solid understanding of calculus fundamentals and algebraic manipulation to do well. For these questions, we also needed to make the right assumptions in order to arrive at the correct solution. Many engineering courses rely heavily on calculus, algebra, and geometry, so make sure to do your best to learn the material in these classes. Now, the first question asks us to find the displacement of two masses sliding on an inclined plane. For the first step, I draw a schematic and calculate the velocity of the mass before and after the collision. Second, I derive the equation of motion and harmonic motion using z of t. Doing some substitution and manipulation, we arrive at the solution here for x of t. The second question involved a system of pulleys, springs, and a dashpot and asked us to find an equation of motion of the mass in terms of x. Doing some kinematics and applying the conservation of energy, we get the equation of motion. If you're wondering what x double dot and x dot mean, they simply represent the acceleration and velocity of the mass. 2 dots mean the second derivative and 1 dot just means the first derivative. Moving on, question 3 asks us to find a damping constant that makes a system critically damped. The system contains a prism submerged in a fluid that's connected to ground via a spring and a dashpot. Critical damping, which falls between under and over damping, just means the minimum value of damping required to prevent oscillations. Now, like always, I begin with a schematic and free body diagram, and then applying Newton's second law and a formula for critical damping coefficient, we get this expression. As you can probably tell, these questions are multifaceted, so I won't go into all of the details. Moving on to question 4, we are asked to calculate the largest force that keeps these two masses in contact. A force is applied to mass 1. Fast forwarding, the final answer is F naught should be less than this ugly expression. Last but not least is question 5. A force is applied to a mass with a spring and a dashpot. We are asked to calculate the damping coefficient that gives the maximum value of the amplitude of steady state response when the frequency equals 1.8 pi hertz. The key to solving this question is knowing which formula to use and what the damping ratio is, which is represented by the symbol zeta here. You probably noticed that this is the only question that has a numerical solution, and all of the others are either in the form of differential equations, expressions, or inequalities. You should definitely expect both types on an engineering exam. Because I showed all my work and was very meticulous, I ended up getting a 93%. The class average was an 80%, and it was worth 25% of our final grade. An exam average of 80% is actually pretty high for this class considering how hard it was. The more I think about it, it does make sense because this class was pretty small and consisted of mostly graduate students. Now, there seems to be a misconception out there that engineering exam averages are very low and that engineering exams are hard to pass. However, that's definitely not the case if you attend lectures, do the homeworks, and put in the work. Alright guys, that's all I got for you today. These were 3 of my more challenging exams in university. Let me know in the comments below if there are any other specific exams you would like to see. If you found this video helpful, check out my video here where I talk about how I would learn mechanical engineering if I could start over. As always, thank you so much for watching, and I'll see you in the next one. Peace.